for being our presenter today. And please start whenever you want. Thank you so much.
Great, thank you, Julia. Thanks for coming, everybody. I hope you're all managing to keep well in these strange times. I'm going to talk about tipping points of the AMOC. And I think the context of this is that the world has moved. So climate science for many years, and arguably including the IPCC process, has really been focused on establishing whether climate change is a kind of phenomenon and the kind of contribution of human activities to it, and establishing that there are some risks that we need to address. And I think the world's moved on really, and we're now really moving into questions about, so what actually do we do about these risks? And that changes the questions, I think, for climate science. And one area where I think it particularly is, this really kind of sort of comes to the fore is in the area of low probability but high impact events. Because quite often these events might be, in terms of the risks, these events might be quite high risk events, even though they're low probability. And I think a lot of focus of climate science up till now has been on quantifying the kind of centers of PDFs and the kind of most likely outcomes. But so this is really this kind of spirit of this is kind of moving on from that in the context of one of these low probability but high impact events. And I should say that what I'm going to show draws very heavily on work by those people that you can see named under there, and you'll see a lot of figures from their papers. So it's the usual story with these things. If you like what I say, you kind of credit them. If you don't like what I say, blame me. So let's move on. If I can move on, wait a minute. There we are. So I don't need to spend a lot of time, I guess, introducing the AMOC to this audience. There's a kind of, I guess you've all seen these kind of cartoons. The only things to remind you of here is that the AMOC in the North Atlantic is bringing warm, salty water northwards into the higher latitude North Atlantic, and it loses that heat to the atmosphere and returns colder, fresher water below the surface. So it's basically bringing in heat and taking out fresh water from the North Atlantic. That's all there probably is to say about that. And then we know that from a whole bunch of modelling studies going back many decades to very simple models and from paleo evidence and so on, that there's at least some evidence that the AMOC has some potential to operate in these kind of multi-stable regimes with thresholds, tipping points, and hysteresis. So this is an example of such a hysteresis in a coupled climate model. So this is the famous model, which is a very low resolution GCM, but it's a GCM nonetheless. It's a low resolution version of the old HADCM3 model. This is from a paper by Ed Hawkins et al. And what they did here was it's a kind of typical experiment. They add some fresh water to the North Atlantic, which we call hosing, which are quantified by this number H. And you start off with the unperturbed state of the model, which is here. H is 0, and the model has a kind of relatively strong AMOC like the present day. You gradually, very slowly increase the strength of this hosing H, and you move to the right on this diagram, and the AMOC weakens a little bit until you get to some sort of threshold where you see a rather abrupt collapse to an off or even reversed AMOC state. And then when you come back, you reduce the forcing, you come back along the blue here, you get this kind of, it doesn't just come back along the same trajectory that it went along, you get this kind of hysteresis where you have to come back a bit further before the thing switches on again. So it looks like we've got this kind of bistable regime of H in here. So that's this is a lot of research has been based on these kind of scenarios, and they're very useful and interesting in showing the sort of interesting structure of the AMOC. They do have a couple of limitations, particularly when we're thinking about future climate change. So the first one is that they're purely driven by fresh water. And of course, we're in a world where we're primarily driving climate change through heating. So what about the kind of heating effects on this? And the second is that this is a kind of quasi-equilibrium thing. So it takes 5,000 years in this run to go around this loop. So we're trying to kind of just look at equilibrium states. And in the real world, we're actually currently increasing the forcing rather fast, so potentially even faster than the sort of dynamical timescales of the system that we're studying. So this kind of slow increase may not be so relevant to transient climate change. And I'll talk about how we're sort of trying to work towards removing those limitations later on in the talk. I think it's probably fair to say that where we can think of this AMOC collapse as a low probability but high impact outcome. So this is the message from my successive IPCC reports has been very consistent. If you look at climate model projections, what you see over the 21st century is typically some kind of decline of the AMOC with some rather large modelling uncertainty in how much that decline would be. But very few, if any, models show a complete collapse. And the latest assessment in the IPCC special report was that the AMOC is very likely to weaken over the 21st century. A collapse, they said, is very unlikely, but a plausible scenario. And you might just deduce from looking at this that, well, it's just not going to happen, because none of the models suggest it's going to happen. So this very unlikely is an assessment by the IPCC authors, taking into account all sorts of evidence and they've kind of drawn back, I suppose you might say, from saying that this isn't going to happen, based on the number of lines of evidence, one of which I'll show you on the next slide. So it's kind of low probability. We know the impact would be high. So this is from some simulations that Laura Jackson did with a relatively recent coupled climate model, where we just artificially kill the AMOC by pouring fresh water into the North Atlantic. And this is just looking at the impacts on atmospheric surface temperature. You can see this widespread cooling throughout the Northern Hemisphere and a small warming in the Southern Hemisphere. But these are large numbers. These are, in the sort of Atlantic sector, we're looking at coolings of between 5 and 8 degrees here. And likewise, there's impacts on precipitation, and this is, again, a typical response from models where you see the ITCZ in the Atlantic move to the south. In this model, we actually see quite a big effect in the Pacific as well. But a general...
Richard, can I ask a question here?
Yeah, go for it, yeah.
So could you elaborate a little bit on the freshwater hosing experiments? That's quite a lot of hosing before you have the shutdown, right? How is that in comparison to what you would get from ice melt in the RCP, say 8.5? Is that the same order of magnitude, or?
So yeah, no, absolutely. So typically with these models, and I'll show some of these later on, you have to put a few tenths of the Sverdrup into the North Atlantic, which is rather higher than anything we would expect from Greenland in the 21st century, which might be more of order 0.1 as a sort of max. Having said that, this model that we're using here, and I'll show you some more results of Laura's from this model later on. This is a kind of prototype for our CMIP6 model, and it seems to be somewhat, in general, somewhat more sensitive than a lot of previous models. So it reacts a bit more sensibly and a bit faster. And I'll come on the next slide to just say why there might be some kind of systematic bias in the way GCMs respond. So that's one of the reasons, actually, that we have a rather deep uncertainty over making statements about probabilities based on this kind of these kind of multi-model ensembles. And I think that's probably one of the reasons that was behind the thinking of the authors coming up with this statement about very unlikely rather than impossible. So I'll come on to that maybe in some future slides. So if we can agree that this is a low probability but high impact scenario, and I'll just show you on the next slide one reason why they might have sort of drawn back from saying impossible. So this is from some work by Jenny Mecking at Southampton. And what she's looking at here is this quantity which we call MOV. So MOV is the, this is at a particular latitude in the North Atlantic, 26 north. And this is the fresh water transport northwards by the overturning circulation. So the overturning circulation is near the surface, is taking salty water northwards, and it's returning fresh water southwards. So that's a southward transport of fresh water. And you can see that all these numbers are negative, which reflects this southward transport. So here's an observational estimate of what we think it should be, around -0.8. And then this is the CMIP5 models. So you can see that at least they are all suggesting a negative transport, which is which we're pretty confident is right. But overall, they tend to underestimate the southward transport or overestimate the northward transport, depending on which way you look at it. And we'll come back to why this is dynamically important in a later slide. But basically, this is a kind of very important diagnostic of the stability or bistability of the AMOC. And the same is true at 34 South, which is the bottom end of the Atlantic. So a lot of attention in the past has been on 34 South, because I think if you're interested in the equilibria, it's the freshwater budget of the whole North Atlantic that's important. It turns out we think that if you're interested in the dynamics of what happens actually at the point where the AMOC tips, then it's actually this North Atlantic value that's more important. But you can see it's the same story here. So the observations are slightly suggest that this is slightly negative. There's a few models which kind of fit in the observational range, but in general, the models tend to have a too positive MOV, which reflects a potentially too stable AMOC. And as I say, I'll come on to the mechanism shortly. Okay, so I want to sort of digress now to a slightly more philosophical discussion of these low probability, high impact risks. As I said, we're moving from a point where we're trying to just establish what the risks are to actually deciding what we might do about them. So how do we manage these risks? So I've kind of taken an analogy of a house fire, which I think is kind of, for most of us, is hopefully a low probability event, but an event that could definitely happen, and it would certainly have high impact if it did happen. So how do I kind of manage that risk in some way? Well, one thing that's probably not terribly useful is to run a whole lot of simulations of a house not catching fire, which is kind of what that is. I'm not saying this is valuable. This is important in that it does establish that this is a low probability event. But actually, a few more model simulations where the AMOC doesn't collapse doesn't really help us to understand things that we might be able to do about the AMOC collapse. So things that you can do for the house fire example, well, you can put in a smoke detector, which is a kind of early warning system. It tells you that there's a fire that's kind of maybe about to get going. And what that does for you is it gives you time to put the fire out, which in climate change terms is urgent mitigation or the reduction of climate change. Or if you can't do that, it gives you time to evacuate the building. In other words, to some kind of adaptation action to avoid or to minimize the damage, at least to you and your family from the fire. So that's something which I can do. In fact, I've already done this, and it's it definitely helps me to manage the risk without actually changing the probability of it happening. The other thing that you can do is to try and change the probability, even if you can't sort of quantify what the probability is. So that's through developing some kind of safe practices. So going about your business or your life in such a way that reduces the chance of such an event happening. And in climate terms, that's this idea of safe operating spaces or safe mitigation pathways. So basically, can we characterize ways that we can control, in the sense, the climate system, the way the climate system evolves, which minimize the chance of an AMOC collapse occurring. So one thing to note about both of these is that in both cases, we don't actually need to be able to quantify the likelihood of the event in order to manage the risk. And that's just as well, because I think, for many years, we were trying to quantify the likelihood of AMOC collapse. And when you've got an ensemble with very few members that actually, if any, that actually show the event happening, it's really difficult to do that in a robust way. So, I mean, I personally have more or less given up on hope of being able to quantify the likelihoods of a collapse in my lifetime, but that doesn't mean that we can't do something about it. So let's kind of unpick these ideas of early warning systems and safe mitigation pathways as they might relate to some scientific questions about the AMOC. So for early warning, the question is basically, could we cross some kind of threshold but not notice that the AMOC had changed yet? And if so, is there something else that we could observe apart from the AMOC itself, which would give us an indication that the AMOC had passed? So that's just the idea of an early warning indicator. If such a thing exists, it needs to have certain useful properties. So, for example, there's a kind of signal to noise question. So how long do you need to be observing your early warning indicator for before you could actually detect that you've crossed the threshold? So if there's a poor signal to noise ratio, you might not detect a change in your early warning indicator until the AMOC was already collapsing. So that wouldn't be much help. So there's a detection time question. There's an adaptation time. So if you did detect that you crossed the threshold, how long would it then take the AMOC to collapse once the threshold was detected? So that's the time you've got to put in place adaptation measures, like, for example, a consequence of AMOC collapse would be sea level rise around the Atlantic. So you might want to adjust your coastal flooding protection. And then the other angle to this is a mitigation angle. So if we cross the threshold, would we have time through some kind of urgent aggressive mitigation actions, like let's say CO2 removal or something, would we have time to draw back before we'd kind of passed a point of no return and we were really committed to collapsing? So we've called that resilience time. And in this, if we were doing this with a live audience, this is the time when I'd show a nice, one of these nice cartoons of Wile E. Coyote running over a cliff, and he goes over the edge of the cliff and he keeps running before he drops down. So he's got some kind of resilience time there. So those are all kind of some time scales that are relevant for this early warning idea. And then on safe mitigation pathways, so here are some relevant questions. First of all, the obvious question is, can we identify a level of global warming that would trigger a collapse? And I would assert that the answer to that is no, or not in any kind of robust way. And that's really a function of the fact that it's a low probability event. And so we can't run an enormous ensemble of AMOC collapse simulations, which is going to actually let us get a really robust handle on that question. As I said in the last slide, that maybe doesn't matter. So there are some other questions that we might be able to answer. So could, for example, too rapid a rate of warming trigger a collapse? Can we get any kind of understanding of that? Or alternatively, there's kind of a lot of talk about overshoot scenarios where we reach some global warming target but allow ourselves to overshoot before we get there. So in this case, is there anything about the rate of mitigation or the rate of coming back below the overshoot that might trigger a collapse if you did it too slowly or even too fast? So there are some questions that we can ask around there. And so what I'm now going to show for the rest of the talk is some progress that we've made on some of these questions over recent years. So one of the tools that I think is very useful to use is some kind of hierarchy of models. So GCMs are great, and they've obviously got the most comprehensive representation of processes and mechanisms, but they do have some problems. First of all, they're expensive to run, so particularly for these low probability events, that creates a bit of a challenge. And also potentially they have, as a class, they have some systematic biases like those MOV biases that I showed you earlier on. So it's useful to have some other tools that we can play with and run very quickly and explore lots of scenarios very quickly. but it's only really useful if we can demonstrate that those tools capture the essential physics that's going on in the more complex models and hopefully in the real world. So this is an example. Sorry, so I know some of you have seen this work before. This is an example that we've developed fairly recently of a very simple box model. These boxes are meant to represent specific and contiguous regions of the ocean. So basically, if you join all the boxes together, you get the whole ocean. And you can see we've got 5 boxes here. So we've got a North Atlantic box where we think the North Atlantic deep water is formed. Then the deep water flows south and spreads out around the global ocean, including the Southern Ocean. So that's this B. Then in the Atlantic, we've got this Atlantic thermocline, this sort of low latitude box, which I've called T, which is the warm, salty water which is being transported northwards into the North Atlantic. And then there's a Southern Ocean surface box, which is generally rather cold and fresh, and an Indo-Pacific thermocline. And I'm not going to go into all the details of the model at this here, but the important things just to note are, first of all, we make an assumption which is certainly justified a posteriori, I suppose, but that the flow, the AMOC strength, which I've called Q here, is proportional to the density difference between this northern and southern box. And I've got an equation of state here which says that basically that means it's proportional to the temperature difference between the northern and the southern boxes here, and it's proportional to the salinity difference between the northern and southern boxes. And these coefficients alpha and beta are just from the equation of state. So that's one simple kind of closure assumption. And then having done that, basically we just do conservation of salt for each box. We actually fix, in this particular version of the model, we fix the temperatures TS and TN, and I'll come back to that later. So we fix the temperatures and we just do salt salinity conservation for each of the boxes. So for example, for this northern box, we've got a ds by dt, d salinity by dt, and it depends on 3 things. First of all, there's advection by the overturning flow Q. So the overturning Q is bringing this salty water in from the subtropics, and it's taking out the fresher water from the northern box. So that's bringing salt in. Then we've got a kind of a gyre term, a wind-driven gyre term, where we assume there's just some constant kind of mass exchange due to the wind-driven circulation. And again, that's bringing the warm, salty water in from the T box, and it's taking out the fresher water from the N box, so just exchanging again. And then finally, there's a surface flux term. So there's a surface flux, which will generally be putting water into this northern box. And there's similar equations for all the other boxes. At each of these boxes, really, we choose the boxes to represent an identifiable water mass in the real ocean or in a GCM. Okay, and then one of the nice things about this model is every parameter in this model, every sort of quotes tunable parameter in this model, actually you can't tune it because you can calibrate it. What I mean by that is that each parameter is a large-scale property of the ocean circulation that you can just read off from, say, a GCM solution or from observations. So we calibrate this model in the things I'm going to show you in a minute to that famous run of Ed Hawkins that I showed right at the start. And the parameters are things like the average salinity in a huge box covering the North Atlantic, which is an observable quantity, and you can just read it off from a GCM solution. So that really is very useful in a way I'll explain in a second. So this is what we've done here. So here, what we're looking at is this is Ed Hawkins's run again. So this is the black dots here are this hysteresis run where we've increased the hosing from 0 up here, and we see this collapse of the AMOC and then a hysteresis as we come back. And then what we've done with the box model is we've basically, as I've described, we can read off all the parameters of the box model just from the unperturbed state. So just from the present day unperturbed state of the ocean. So that sets all the box model parameters. We then just run exactly the same experiment in the box model where we increase the hosing and decrease it, and we see a similar hysteresis, obviously not identical, but there is some kind of quantitative skill in this model. But it has the same kind of hysteresis effect. And actually, if you dig into the dynamics a little bit more, you actually find that it's probably getting the right answer for the right reason here. So what we're looking at here is the salinities in those 5 boxes as a function of time as we go around the 5,000 years of this hysteresis experiment. So this is the point here after about 1,000 years where we get the collapse. And so basically this is the time series of the salinities in the GCM, and this is the time series of the same salinities in the box model. And this is the entire state space of the box model. There's nothing else in the box model. And so what you can see is that not only is it capturing the hysteresis, but it looks like in some sense it's capturing the large scale dynamics of what's going on in the GCM. So that gives me some confidence that this box model is actually capturing the processes that are going on in the GCM when we run it through this hysteresis loop. We can go into that in a bit more depth. I'm going to go fairly quickly through this, but basically we can construct a salinity budget for this northern box here, just using this equation here. And as I said, it's got 3 terms. It's got this advection by the overturning itself. This is the green one. It's got this wind-driven exchange, which is the blue, and it's got the surface fluxes. So these are these terms as a function of time. And you can see that as we gradually increase the hosing, the surface flux term is negative, it's freshening. And as we increase the hosing, it gets more negative. So that's just an imposed forcing. And then what you can see is that as we go through the first stage, really these are, this freshening is slightly compensated by the wind-driven mixing. So the 2 boxes are just mixing out. The wind-driven mixing is just mixing out that fresh water that you're putting into the north. And this advection by the overturning, which is minus this MOV term, is more or less constant. But then at some point where you get near this threshold, you see this sudden kind of tip over a cliff. And basically that's because this advection of salinity is quadratic in Sn. So remember, we've got Q times Sn here, and remember Q is proportional to the salinity difference between the northern and southern boxes. So Q has an Sn term in it. So there's a quadratic in Sn, and that's what basically at some point gives you this nonlinear behavior, which basically gives you a positive feedback and takes you over the threshold to the off state.
Can I ask another question?
Go for it. Yep.
Okay, thanks. So I have actually 2 questions. The first is related to this wind mixing term.
Yeah.
Which is like a flow here. I mean, usually one would model that as a diffusive term. What would be the difference here? I mean,
it sort of is a diffusive term. I mean, it's a down gradient transport of salinity at a particular rate. So the Kn is like a diffusive velocity, which I like to think of as, in some sense, the strength of the massive. So the gyre is taking salty water northwards, or typically on the western side of the basin, and bringing fresh water southwards on the eastern side. And so the strength of the gyre, it's like a kind of diffusive velocity. So I do think of that as a kind of diffusion.
Turbulence flux. Okay.
Yeah.
Then another, maybe this is just too technical. I noted in the box model, when you go back to the on state, you have an overshoot.
Yep.
And where does that come from? Is there inertia in there?
Yes, there is. We'll see that maybe in a minute. Yeah. Well, I've got some trajectories in a minute, which kind of show that in a slightly different way. So maybe we come back to that at the end if you don't, if you want to talk more about that. Okay. So basically this quadratic dependence really depends on whether this MOV term is positive or negative. And if MOV is negative, which it is here because this is minus MOV, the AMOC's exporting fresh water from the northern box. And then as you weaken the AMOC, it exports less fresh water, so it gets fresher still. So there's a positive feedback here. If this was the other sign, then it would be a negative feedback, and everything would be very kind of boring and stable. Okay, so we've got some understanding, some dynamical understanding of how this is operating in the box model. It turns out that Laura had already done a similar analysis for the famous model itself, basically constructing salinity budgets, and I've kind of converted that into the same colours and the same scale on the figure, and you can see that basically the same thing is happening in the GCM. So you see this green term, which is more or less constant until we get to some kind of point where it goes past the threshold, and then it accelerates. In the GCM, there's also a few feedbacks through the atmosphere on the surface pressure water flux. But again, basically, this is saying that we're capturing the dynamics of that transition to some extent. So actually, that gives us almost immediately a candidate early warning indicator, because remember, we can determine the box model parameters from just the present day state of the ocean. So you could do that, and then you can run your box model through this hosing scenario to try and estimate how much hosing is needed to get to the threshold. And potentially that's quite nice, and then potentially it works. So we've actually got 3 different versions of this famous model where we've done the hosing now. And so this is just showing the kind of the ramp up phase of the hosing. So just where the hosing is increasing. You can see these 3 different versions give 3 different values for how much hosing you need. And then when you calibrate the box model to the 3 different states just in the unperturbed state, you can see that at least qualitatively it's giving you some idea of how the amount of fresh water needed varies with the state of the ocean. So that's kind of encouraging. It's not perfect, so there are certainly some quantitative errors, especially for this brown one here. And again, we come back to these things that this is only proven for sort of quasi-equilibrium, very slow increases in the forcing so far. And questions about, does it apply to warming scenarios? So is there something that we could do that's a bit better and more robust than this? So this is where we started working with Peter Ashwin and colleagues, which proved very productive. So that turned out that they were interested in this same sort of non-autonomous problem where the system itself, or the forcing of the system, is changing as fast as the dynamics. So Hassan Al-Khayron, who's a PhD student working with Peter, did some analysis of this. So this is an analysis of the 5-box model. And what we're looking at here is the equilibrium states as a function of this hosing H. And some of this looks familiar from the kind of simpler models. So over on the left here with low H, we've just got a strong on state. Over here we've only got the off state for high amounts of hosing. And then in between, we've got these multi-stable regimes, but it's a bit more complicated than the sort of simple 2-box models. So, and so I'll show you maybe through so there's some more interesting bifurcations here, and I'll show you through by showing the trajectories. So, so what we're going to look at here is some trajectories in SN and ST space. So this is the salinity of the North Atlantic, and this is the salinity of the subtropical Atlantic. And the important thing to note about these is that these are things that we can measure. We can observe these things now, and we pretty much are observing these things now. So this is potentially, we can potentially observe these trajectories in the real world. So here we are in this kind of left-hand regime, and it's pretty boring. We've only got one equilibrium state, which is shown by this blue dot here. It's got relatively high salinity in the North Atlantic, and generally high salinity in the North Atlantic means a strong AMOC, low salinity in the North Atlantic means a weak AMOC. And all the trajectories do the same thing. They kind of spiral into this. Wherever you start, you spiral into this equilibrium. So that's where those kind of overshoots come from. If we move on to the next regime here, so now we're in a multi-equilibrium regime. We've got these 2 stable equilibria and this what I've learned to call melancholia state in the middle. So those 3 equilibria are shown here by these three dots. And you can see that if you start somewhere near the strong AMOC state, you still just spiral into it. If you start somewhere down here, you end up in the off state. And if you happen to start on this line, you end up going into the melancholia state. And then we've got these more interesting bifurcations. So at this point, this kind of semi-infinite attractor collapses to a finite attractor for the strong state. And as you go to the right, as you increase H, this attractor becomes smaller and smaller. But if you start in here, you still spiral clockwise into the strong state, but the attractor of the off state is getting much bigger. And then you pass this top, and now at this point, this is still a solution, but it's now an unstable solution. So now you've got an equilibrium here, but even if you start very close to it, you spiral away from it and spiral to the off state. And then finally, over here, you've only got the off state, so all roads lead to Rome for the off state. So an interesting kind of property of these trajectories, if you have a look at these. If you look at any trajectory that has an anti-clockwise curvature, so all these spiraling into the on state that go clockwise, if you have a trajectory that has an anti-clockwise curvature, it's always going to end up on the off state. So this suggests a potential early warning indicator, which has the nice property that it's completely qualitative. So it doesn't depend on any real kind of quantitative skill in the model. It's something that we could observe, and basically what this is saying is if this is the underlying dynamics, then if you observe a trajectory with anti-clockwise curvature, you're going to end up on a collapsed AMOC state. So I like this more than my previous early warning indicator because of this kind of qualitative nature. So it seems potentially a bit more robust. I'll come back to that in a minute. So kind of encouraged by that. That then raises these questions of the adaptation time. If you could get an early warning indicator, how long would it take for the AMOC to collapse? And so this is some work that Laura did with, again, this sort of pre-CMIP 6 version of the UK climate models. And so what she's done here is just turned on some hosing at time 0 of different strengths, 0.1, 0.2 and higher here, just to look at the time scales of collapse. So you can see with weak hosing, even with 0.1 Sverdrups, actually, the AMOC seems to be going down to a very weak state, but it takes a long time to get there. But then as you get past about 0.3 of a Sverdrup, everything seems to converge on this kind of initial phase of fairly rapid collapse in about 40 years, followed by a slower reduction after that. In the paper, there's a fairly detailed analysis of the mechanisms for why this is, and it involves some quite complicated gyre processes, which certainly aren't in the box model. But that's but at least that's suggesting that there is some kind of time that's non-zero after you've kind of committed yourself to an AMOC collapse that you've actually got to respond. And then there's this resilience time as well. So we looked at this both in Hassan's work and with Laura's work. So this is this question of if you increase the thawing beyond the threshold, have you got time to come back? So to look at this, we've got these scenarios where you turn the hosing on over some period of time, you keep the hosing on, and then you decide, oh dear, I don't want that hosing anymore, I'm going to take it away. Do you come back to the on state, or is it too late? So Laura's got some experiments with this GCM again, where she's turned, this is a case of 0.2 Sverdrups hosing. So if you leave the 0.2 Sverdrups hosing on forever, that's the grey curve here, and you see the AMOC seems to collapse to about 2 or 3 Sverdrups. But then in these other experiments, she's left the hosing on for a certain length of time and then turned it off. So the green, it's turned off after 20 years, and you can see we recover. The blue, it's turned off after 30 years, and again it recovers. This kind of yellow, it's turned off after 40 years, and again it looks like it's recovering. But if you keep it on for 50 years and then turn it off, ooh, it looks like it might not recover, and it might end up somewhere down here. So this one looks like it's almost on a bit of a cusp, actually. and we'll come back to that in a second. And of course, yeah, and so you can do similar experiments with the box model. So here are two scenarios with very similar. I think the difference between those is in the length of time that this H-PERT, the length of time that the hosing's been maintained, and you see, and obviously there's some kind of threshold length of time where if you come back soon enough, the AMOC recovers, and if you just go over that time, you're committed to being off. So this is getting us some feel for this resilience time. And again, so Hassan did these kind of fairly lengthy experiments where he held the hosing on for different lengths of years, 220, 225, 230 years. This is this SNST phase space again. So here's the on state. You turn the hosing on and you kind of creep down here. If you turn the hosing off after 220 years, you spiral back into the on state. If you turn it off after 235 years, you end up spiraling into the off state here. So again, there's this kind of critical resilience time. And these are the trajectories from Laura's experiments with the GCM. So we see that when you turn that hosing off after 20 years, the AMOC came back, and you can see it spiraling back. 30 years, it's spiraling back. 40 years, it's spiraling back. 50 years, whoa, not sure. We'd really like to run this on for probably a few hundred years more, actually, to see which way that goes. It really does look like it's on the cusp, but it looks very similar to the trajectories we get. Okay, now I'm going to have to move on. I'm going to skip some of this rate-induced tipping because I'm going to come back to that. So, so all that work I've just been talked about is published in a couple of papers that I've got the references in here for. I just want to move on to share some work which is very much work in progress with this box modelling to try and move it towards these more realistic scenarios, particularly warming-driven scenarios rather than things that are just driven by hosing. So actually, even with the existing box model, we can do something here. So I've already showed you these figures earlier on. Remember, I said these are three different states of the model, and actually the blue state and the sort of brown state, they're basically the same version of the famous model, run to equilibrium at 1 times CO2, so pre-industrial CO2, and then we did the hysteresis experiment, and you needed 0.45 of a Sverdrups to kill the AMOC. And then this is the same model, but it's now spun up at double pre-industrial CO2, so it's a warmer climate. And then having spun it up, we do the hysteresis experiment, and it turns out in the warmer climate you actually need a lot more fresh water to kill the AMOC. And the same is, the box model sort of reproduces this result when you calibrate the box model to the 1 times CO2 or the 2 times CO2 state. So the nice thing about the box model is that then you can unpick the parameters that are different between the 1 times CO2 and the 2 times CO2 state to give you some kind of insight, physical insight, if you like, into why this threshold has changed. And there turn out to be 3 factors, and the first one, at least, I think is extremely robust. So basically, the first reason why this is that in a warmer climate, we expect the overall hydrological cycle, the water transports in the atmosphere, to increase, which means the Atlantic basin, which is already an evaporative basin, becomes more evaporative, and because that's the kind of salting of the Atlantic. And that pretty clearly leads to a move of the threshold to the right. The other 2 things that seem to be playing a part in this move are sort of changes in the thermal driving, but this isn't really properly thermally, it hasn't got a proper thermal variable in the model, and changes in these gyre transports. And I think these things are a little bit less robust. But having said that, we have at least tuned the box model to a different GCM. So this is a CMIT5 GCM at 1 times CO2, 2 times CO2, and 4 times CO2. And again, the threshold moves to the right as you go to warmer climates, and that this strengthening of the water cycle seems to be a key factor in that. So this is still equilibrium thinking, so it's still not really relevant.
Richard, quick question.
Yeah.
This question of stability at higher CO2, that only applies to the steady state. You produce a steady state at 4 times CO2 and look at the stability. It may not apply to a scenario where you go, say, in 1% per year to 4 times CO2, but you start from 1 or 2 times CO2, right?
Exactly right. Yes. So that's why I want to do something better than this. So that, which is
Okay.
the next slide. Yeah, absolutely. So what I've just been trying recently is basically to extend this box model, which works quite well for these hosing scenarios, to include an active thermal variable so that we can force it with increasing CO2. So basically, the model is very similar to the one I just showed you. There's a slight change in the geometry, but not the topology of the model, in that this North Atlantic box now really only represents the top few hundred meters of the North Atlantic. It doesn't make a big difference for the hosing scenarios, but it's important for warming. So then I just do conservation of heat for each box. So again, we've got advection by the overturning, we've got this gyre term, and then we've got some surface flux terms. So there's a basic surface flux, and then I'm allowing myself to apply some radiative forcing, for example, for increasing greenhouse gases as a function of time, and applying some kind of climate feedback parameter, which is like 1 over the climate sensitivity. So this is a very standard way of doing energy balance modeling for global warming. And then the other thing I want to do is make the water cycle dependent on the temperature. So I'm basically scaling the amount of fresh water that comes out of the tropical Atlantic and goes into the north and south boxes proportional to the temperature, and also allowing for some temperature dependent input of fresh water from some supposed Greenland ice melt into the northern box. So that's how I'm trying to model a more transient climate change scenario. Basically, the stage I'm at with this is trying to convince myself that the model is doing some, is reproducing some known GCM results. So this is a paper from a few years ago, which Laura led, looking at a number of different GCMs, where they've run them through these kind of ramp up down CO2 scenarios. So in each of these cases, the CO2 is ramped up to some increased value. It's held at the increased value for some years, and then it's reduced again. And what we typically see in all these models is that when you're ramping up CO2, the AMOC weakens. Well, you know, we've known that for a very long time. When you stabilize CO2, the AMOC generally has a very slow recovery. And then when you ramp the CO2 down, I'm looking at this blue curve, for example, when you ramp the CO2 down, there you get a very rapid recovery of the AMOC, and it overshoots the original value before eventually settling down. And this slow recovery is mostly salinity driven. So this is basically the fact that the North Atlantic, because of this enhanced water cycle, is slowly getting saltier, and that drives this recovery. There are some temperature effects in some models, but mostly this is salinity driven. And then when you ramp the CO2 down, what they show in this paper is that basically there's a whole lot of salty water stored up in the subtropical Atlantic, which then gets released to the North Atlantic in a transient way, which gives you this sort of rapid overshoot of the AMOC, which comes back down. So I'm trying to reproduce some of those results with the box model. I'm going to go very quickly through this and not go into any detail, and this is work in progress. But so what I've done here is I've reproduced one of those figures from the previous plate. So this figure here using FAMOUS. I've reproduced that figure for these ramp up and down scenarios for FAMOUS. And then I've tried to reproduce the black scenario actually in the box model. So this is the AMOC response in the to be compared with the black AMOC in here. So there's a spin up phase in this model, but then in the ramp up phase we see an AMOC decrease. In the constant 4 times CO2 phase, we see a recovery which is actually rather stronger in this model than it was in FAMOUS. And then we do get an overshoot when we ramp the CO2 down. It's not nearly as strong as it was in FAMOUS. So there's some differences here which I need to dig into more to understand. But broadly speaking, and so because again you've got all the variables in the box model. So this is the temperatures in each box and the salinities in each box. You can really unpick the mechanisms that are driving this. And if you read Laura's paper, she's already unpicked the mechanisms that are going on in some of the GCM runs. So this is really, so there are some differences. So some of this recovery, for example, is more temperature than salinity driven in the box model. But at least some of the qualitative behavior gives me some confidence that with a little bit of extra work we can do, we can use this model to do some interesting things and some credible things. And so that hasn't stopped me from trying to do something interesting before I've really proven the model. So this is just an example of some rate dependent tipping in response to a CO2 increase. So this is a slow ramp up of CO2 to 4 times CO2. If you do it slowly over 150 years, the AMOC collapses, but then when you stabilize at 4 times CO2, it partly recovers. If you do the ramp up really fast, then it kind of collapses completely and it stays off. So there's a rate, it's the same CO2 concentration in both these cases, but there's a rate dependent tipping. I should say you have to make Greenland respond very strongly to make this happen. So this is not the first time that somebody's shown a rate-dependent tipping down. It's great to hear you here, Thomas. So this is from a very old paper by Thomas and Andres Schmittner, where they showed a very similar behavior in the burn EMIC at the time. So if we just look at, say, the red scenarios here, where they're increasing CO2 to a particular rate, either slowly or rapidly, and you can see if you go slowly, which is a solid, the AMOC recovers, and if you go rapidly, it doesn't recover. So this is one example of the sort of kind of safe mitigations pathways work that yeah, I'm hoping that we can take forward a bit with this model, and particularly within TiPES. Okay, so I'll sum up then. So first of all, I would claim that it's certainly not feasible, and I would claim not even particularly useful to estimate the probability, given that we know it's low, of crossing an AMOC tipping point. So it's a low probability, high impact event. But to manage the risk, you don't actually need to estimate the probability. So what we have done is we've used this traceable hierarchy to understand the risks and how to manage it. And it may be, certainly from those clockwise and anti-clockwise trajectories, that some really simple system of observing the Atlantic salinity may provide some early warning indicators of an AMOC collapse long before it happens. So we've made some progress in understanding, in GCMs, in understanding this resilience time and the adaptation time. We haven't done much on the detection time yet, and that's something that we do need to do some work on. And then also we're sort of starting to look at this question of safe mitigation pathways, for example, rate-dependent tipping, but that's definitely work in progress. So I would say we've got a good framework here that we've developed over recent years to understand the dynamics of actually crossing the AMOC tipping point, particularly in response to hosing, and that's largely been developed in these famous and GC2 models. But there are some really, questions here. So obviously, do these insights apply to other models? What are the limitations of the insights? And what about there are many other ways of looking at this problem, I'm sure, that might give different insights. So some things that I'm keen that we do, first of all, is that if other groups are interested in calibrating their GCM runs, where they've got some hysteresis runs, calibrating the box model to the GCM, to their GCMs, I'd be really interested to have a chat with you about that. And then also on the last slide, which is the next one, Laura's got a proposal for a GCM MIP to look at this in more detail across a number of GCMs. So sort of questions we want to ask there, how robust and how practical are these early warning indicators? And as I said, moving towards these more relevant scenarios driven by greenhouse gas warming. So this is the final slide. This is just to advertise. Laura has a proposal for a new MIP. So the objective is this here, basically it's based on these sorts of experiments that I showed earlier, where you kind of hose for a bit and then turn the hosing off. So can we use these models to understand the signs and the strength of the key feedbacks that control the AMOC hysteresis in order to better understand the likelihood or ways of managing the risk in future? So if you're interested in this, and I hope people running GCMs will be really interested in joining in with this, and maybe we can do some of this within TiPES, please contact Laura at the address below. And that's it. Thank you very much for listening.
Thank you, Richard. Great.
Thank you very much. So questions, comments, feel free to ask or to write them in the chat box.
Oh, yeah.
Please go ahead.
First of all, I think this is a really nice study employing the full hierarchy of models, and that's always something that I liked, going back and forth across the hierarchies. I have one question regarding the diagnosis procedure of these key parameters in the box model. I didn't quite understand that, because I think that's really the secret of formulating a box model. I saw how you more or less identified the water masses. That makes a great deal of sense. But how do you then estimate these transfer parameters of the heat fluxes, of the salt fluxes, etc.? How robust are these estimates? And I presume that they really strongly determine the dynamical behavior of the box model.
Yeah, they do. So in a sense, it is rather easy. So for example, let's take an example of this lambda here. So that's a kind of pipe constant, if you like. So within a GCM or potentially within observations, we can measure these bulk temperatures and salinities. Okay. The alphas and betas just come from the equation of state, so they're known, and we can measure Q. So basically, the way I estimate lambda,
it's a correlation analysis.
Yeah, well, it's even cruder than that, to be honest. I just take the present state of the ocean. I say Q. I assume it goes through the origin, and I go and I say I take the present state of Q, and I take the present state of those numbers, and basically, with possibly one exception, which is the kind of warm water path, cold water path parameter, which is maybe a bit more tuning, but basically. All the parameters in this model can be just read off from emergent properties of the circulation. So.
Okay. The other question I had, I think this initial response of the Greenland ice sheet is a great way to enhance the freshwater flux, and this is key to the whole story. But we're now also increasingly concerned about freshwater flux from Antarctica. And I think that shouldn't be forgotten, that this is a big potential driver as well. And I wouldn't be able to say off the cuff in which direction that goes. Is it more stabilizing or not?
Yeah, that's interesting. So I know there are some studies which do hosing in the Southern Ocean.
It's more in the paleo context, though.
Yeah.
I don't remember one for the future evolution.
I think I have seen one or two for present
really?
day. But I'm not sure they've done. But it's more hosing. What's the impact on the AMOC rather than any of these sort of hysteresis type studies.
Okay.
So, yeah, that's a good question. But absolutely. I mean, a lot of this, I should say, when I kind of started playing with this model, I thought this could be really useful for paleo. We don't do much paleo at the Hadley Centre, so it's not our primary interest. But what I would say about it is, if I go to the next slide, is that this model does quite well for this right-hand threshold. It does less well for the left-hand threshold. Which may be a paleo relevant one, and the reason for that is that we have to fix the boxes according to present day water masses, and of course if you in the GCM, once you've gone past the right hand threshold and collapsed the AMOC, the water masses start changing, so the box definitions start to become, you need to change the boxes, and that
right. Okay.
So I think this is more useful for the right hand threshold, but still potentially has some qualitative value for things that might be going through the left-hand threshold as well. Certainly interested in if anybody who has got some paleo runs, that they'd like to get some box model parameters for. Be interested to talk about that.
Thanks.
So I can't see the chat at the moment, so I'm not sure if there's a.
Maybe I can ask a question. Oh, sorry, Niklas.
Go ahead. It's fine.
I was wondering, So thank you very much first for the interesting talk. I was wondering, you said that you would like to include freshwater forcing from Greenland. And I was wondering how you would like to do that in your box model.
So at the moment, all I'm doing is adding, where are we? Oops, next one back. All I'm basically going to do is add some fresh water into this northern box, which I make proportional to some measure of either the local temperature or the global temperature. So I just have a constant here, and I just say extra fresh water flux into the northern box proportional to some temperature variable. That's sort of, you know, that's the level of sophistication which I think is appropriate for a model of this, you know, that's this simple.
Yeah, sure.
And I should say also that at the moment, I haven't yet, with playing with this model, been able to collapse the AMOC without having with kind of transient CO2 increase, without having a significant amount of freshwater input from Greenland. I'm perhaps not surprised by that. So whatever I've done in terms of transiently increasing CO2, I can't get enough fresh water into here to collapse the AMOC before the whole North Atlantic has already got salty enough to stabilize it.
Okay, thanks.
Hi, thanks, Richard. This was really interesting. I had a similar question. So if I understand correctly, so far the model is calibrated only with respect to the GCM simulations. Is it possible to do this also to really take observed quantities? So to really calibrate it against the real world?
Yeah, in principle it is. And in fact, in the paper, we do calibrate it, as well as calibrating it against FAMOUS, we calibrate it against an ocean reanalysis. It comes up with a threshold which is slightly further over to the left in that case, but still quite large, you know, in terms of Greenland fresh water. It's sort of around 0.3 Sverdrups or something like that. I would like to do something a bit more thorough on that. I hesitate to sort of make grand statements about that. That's where the threshold is in the real world, without really understanding the uncertainties in the observations, and then quantifying the model error and adding that in as well. So that's potentially a future project, but it needs some pretty serious work.
And can you give some rough estimate? What I see here is the threshold is around 0.45 Sverdrup.
Yeah.
How much of the Greenland ice sheet would that correspond to? Or of all the freshwater sources that go into the North Atlantic?
So as far as I'm aware, I'm no expert on the Greenland ice sheet, but as far as I'm aware, for the 21st century, 0.1 Sverdrup is about a sort of a rough kind of upper bound for the kind of rate that we might get in the 21st century. So, but having said that, I will also say that, you know, just sort of re-emphasize that for this GC2 model, which is a more, you know, this is our CMIP6 model, nearly our CMIP6 model, you know, even 0.2 has something, so I know if you run it for long enough, 0.1 will kill the AMOC. So this model does seem to be quite sensitive compared to some previous models. And I don't have an explanation for that. You know, of course it's a more recent model, so we think it's better overall. But I wouldn't just leap in and say therefore it's right. But I think, you know, I think if you look at this one, actually, this is quite interesting. So this is where these things come back. So in the box model, and we think in FAMOUS, you know, this timescale is hundreds of years, and it's probably some kind of big flushing time for those boxes. But in the real ocean, and potentially in some more sophisticated GCMs, you can probably short circuit some of those things, because maybe if the ocean stratifies, you only need to solidify the surface layer of the ocean, or you only need to warm the surface layer of the ocean to make something happen, rather than the whole top 800 meters. So in something more sophisticated than a box model, and maybe in some higher resolution GCMs, it may be that actually these flushing times are much shorter, effectively, than they are in the box models. So that's one thing I hope to understand with this thermal model. understanding the differences between the GCM and the box model.
Thanks.
Okay, I think that's all. If there are no more questions. Okay, thank you so much everyone for joining us, and please remember that the webinar is recorded and will be uploaded on the website. So please fill in the form and return it to me, okay? Thank you very much. We'll be in touch. Thank you, Dr. Wood, for...
Thanks everyone.
Thanks,
Thanks,
Richard.
Richard.